All right, and also the recording. So once again, welcome to the webinar. And our speaker for today is Yonina Eldar. And her talk is going to be on model-based deep learning with applications to imaging and communications. I'll run through a brief bio. She's a professor in the Department of Mathematics and Computer Science at the Weizmann Institute of Science in Israel, where she heads the Center for Biomedical Engineering. She was previously a professor in the Department of Electrical Engineering at Technion. And she is also a visiting professor at MIT, a visiting scientist at the Broad Institute, and an adjunct professor at Duke University. And she was a visiting professor at Stanford. She received her BSc degree in electrical engineering from Tel Aviv University and her PhD in electrical engineering and computer science from MIT in 2002. She's a member of the Israel Academy of Sciences and Humanities, an IEEE Fellow, a EURASIP Fellow, and she has received many awards, including an IEEE Signal Processing Society Technical Achievement Award, the IEEE Kyo Tomiyasu Award, and numerous other awards that are in her bio. She has received several Best Paper Awards and Best Demo Awards with her research students and colleagues, and was selected as one of the 50 most influential women in Israel, and was a member of the Israel Committee for Higher Education. She's the chief editor-in-chief of Foundations and Trends in Signal Processing, and a member of several IEEE technical committees and awards committees. So, so with that, we would like to welcome her again to the SPACE webinar, and I very much look forward to her talk. Just as a heads up, normally if you want, you can stop in between, Yonina, and answer questions. The audience would post questions in the Q&A tab, and I encourage the audience to use the Q&A, not the chat, because questions may get missed. Also, we could just wait until the end and answer questions in the end, and we typically also enable people to speak up and enable their microphones so they can interact with you on their questions.
Yeah, so I'd love for people to just feel free. It will be hard for me to read the Q&A while I'm talking, but please do feel free, ask questions. It will make it much more interactive, and I'm really happy to take questions as I'm speaking. So I much prefer that, and feel free to just open mic and ask, if that's okay with the organizers.
Yeah, that's totally fine. And would you like to read the questions yourself, or sometimes we just read the questions out for you and handle all of that so that you just answer them?
Okay, so perfect. If you see a question, just read it out. Stop me, read it out, and I'll be happy to try and answer.
Wonderful. And if you need to take some water or anything in between, given that you have a throat, that's totally fine. Don't worry.
Okay, thank you. I may need to, so thanks. Okay, great. So thank you very much. Good afternoon, or good morning, or good evening. I guess it depends where everybody is. And thanks very much for that really kind introduction. Before I begin, you can hear I have a really bad sore throat. So hopefully I'll last throughout the talk. So I apologize for that. I hope I'll still be interpretable. And I guess one of the advantages for those that know me is that with this sore throat, it's going to slow me down because I need to stop and breathe more. So I guess that's a good thing. Hopefully I'll talk slower. All right, so it's really an honor and privilege to be able to give this talk, and I'd like to thank the organizers both for inviting me and for accommodating the time change with all the holiday breaks now in Israel. And there's many, of course, disadvantages and major hurdles with this pandemic, but I think one of the advantages is these types of seminars, that we get an opportunity to interact and to talk to people that we normally wouldn't get a chance to do that. So I'm really happy for this opportunity. And as much as I'd like to have the opportunity to meet everyone in person, I hope we can have more opportunities like this to give seminars and interact. And do please feel free to make this interactive. So, the more questions, the happier I am. So good. What I'd like to talk about today is how we can try and merge traditional model-based learning methods that we're all used to from signal and image processing with deep learning, where the goal is to try and obtain, very efficient and interpretable methods for different problems. And today I'll focus on problems in imaging and communications, but of course, these ideas could be used more generally as well. So as we all know, in the past decade, deep learning has revolutionized many fields with huge empirical success. And especially it has been successful in problems that are difficult to tackle using conventional optimization methods. Two leading examples, of course, are computer vision and speech processing. Now we know, of course, that we've reached, unprecedented empirical success. We could span, fake faces. There's a lot of cool stuff we could do with deep learning, but there's also some drawbacks. So first of all, we often need very, very large training sets. It's not really clear how interpretable the methods are. So, as this cartoon shows, often it feels like we're mixing everything we have into some bag and just we continue to mix until something good comes out. We know that the training could be computationally very exhaustive. So again, another cool cartoon is, the number one excuse for a data scientist for slacking off is that my model is training, right? So that could go on for a very long time. We don't know how robust the methods are. We don't know how well they generalize. And even when the methods work very well, like the GPT-3 network, it has billions of parameters. So these are really a huge number of parameters to learn and to comprehend. Now, on the other hand, when we look at signal processing, right, or at least traditional signal processing, things are, very model-based. So we rely on a model. It's very easy to incorporate domain knowledge and structure. We could infer from small amounts of data, and we also have very nice analytical techniques to assess the quality of the output. So these are all the advantages of signal processing, but of course, it has disadvantages as well, and that's the first disadvantage, of course, is that we have to have very accurate model knowledge in order to be able to have these advantages that we just outlined. The second is that the inference can be rather slow, so it's not always so efficient. So really what we'd like to talk about today are some ideas that we, and of course many others, have been working on, and mainly to open for, maybe more thoughts and more discussion on how we could kind of try and combine these two. So how we could combine model-based algorithms with deep learning algorithms, where really the holy grail would be to get methods that are compact, small enough, deep, but not too deep, interpretable, simple to train, but still data-driven. So we're still exploiting the information we can from the data. So that's really kind of the goal of what we'd like to achieve today. And I want to illustrate, some of these concepts in a very simple example taken actually from the communication space. So, one of the basic problems in communication is to be able to decode symbols that are transmitted over some channel. So, we have a transmitter, we have a receiver, we have some channel. In this case, it's a MIMO, multiple input, multiple output channel. And, the transmitter is going to transmit some symbols S, the receiver receives Y, and we want to be able to decode S. Okay, very standard basic communication problem. Now, there's of course many established model-based methods for doing this. And what all of these methods do is that they start with assuming some known simplified channel model. So for example, the easiest model to look at, and a lot of the algorithms used today are based on this model, is just a linear Gaussian model. So we model the channel by some matrix A, and we have some additive noise. And then once we have this model, we could go ahead and compute our favorite metric. So for example, we could compute, the maximum likelihood or the maximum a posteriori detector, and then we get our desired symbols detected. So the advantage, of course, is that we have an optimal receiver. The disadvantage is that it's very simplified. So the environment may not really be modeled accurately by the simple linear Gaussian model. And of course, we have to know the channel. So in practice, what we do is that we repeatedly estimate the channel in order to be able to apply these types of algorithms. So what could we do instead? Well, we could use the advantage of deep learning. We could simply get rid of the symbol detector, these nice model-based methods, and replace it by a deep network. And of course, there's been many works in recent years which have done precisely that. But the disadvantage of that approach is that it's going to require large training sets, whereas in reality, channels could change very rapidly. So if we train for a certain class of channels and then, the car is moving, the channels could change and the deep network may not work. It requires many, many parameters in order to get good symbol detection. And this may not be relevant if we think of edge devices where we want to do things very rapidly and very efficiently. And of course, I guess, coming from a signal processing point of view, one of the things that is kind of the least satisfying is that we know that at least when the channel is known, we have optimal approaching algorithms, right? We know what the optimal thing is to do, and we replace everything by a deep network. We no longer could guarantee anything, even in conditions which are stationary. So even when we can estimate the channel, we no longer could guarantee optimal performance. So somehow what we would like is something more gradual, right? So we'd like something that when everything is known, we're down to the model-based method. And then when things become unknown or changing, we slowly learn from the data, but never get to black box mode. Okay, so we want to kind of start with the model-based framework and add learning as needed, but not more than needed. And this is kind of the approach that we're going to try to introduce today. And of course, many people are working on this, and there's many beautiful works out there trying to promote the same approach. So I would view this less as, just the specific results that we're showing, but more as a framework that I think is a huge opportunity for people, like us who are coming from a signal processing or image processing point of view. So just as an example, and we'll see more details, of course, throughout the talk, this is a model that we've developed, a receiver that we've developed called ViterbiNet, which is basically based on the Viterbi algorithm, the most popular algorithm for symbol decoding, but we allow learning within the Viterbi model so that we coincide with Viterbi when the channel is known, but we allow for a minimal amount of learning when the channel isn't known. And unsurprisingly, it works very well. It works better than generic deep networks, and it approaches the performance of Viterbi even when we don't know the channel. So we'll try to explain throughout the talk how we get to these types of performances. So, and again, I apologize for those joining now. I really apologize for my voice. I woke up with some sore throat, but hopefully you could still hear me. If you totally lose me, then somebody be brave and let me know. Okay, so in order to kind of progress and think about how we would merge these two ideas, I want to give like a bird's eye view of model-based signal processing versus deep learning. And this illustration will serve the purpose of showing us how we could go ahead and combine these ideas. So in standard signal processing, typically we start with a measurement. So, we have some input, we'll call it Y. We have some output that's desired, we'll call it X. And in between, we have some model. So we're going to assume that we know in advance that Y is approximately equal to G of X. So that's our model. And then we're going to come up with some metric. It could be, let's say, the difference between Y and GX, some norm of that difference, or some other metric that's going to measure proximity of Y to G of X. And then we're going to optimize that. So if it's a error norm, we're going to try and minimize the error, and in that way recover the desired X. So typically, this is not going to have a closed form solution. We're going to have some iterative algorithm, which is going to look something like this. So we'll start with some generic mathematical operation. We'll then go through some iterative algorithm, which typically has some part that's generic, and then some part that depends on the model, which we don't necessarily assume that is known when we think about learning. And then we're going to have some post-processing and get our output. So this is kind of, an illustration of what we would typically do in signal processing. Now, on the other hand, if we think about deep learning, the story is very different. So we're going to assume that we have training data in supervised deep learning. We have many inputs, Y, and many outputs, X. We're going to use them to train a fixed network that is determined in advance. This network has nothing to do with our underlying problem. We're going to use it to train the network parameters. And then we're going to hope that when we input a new observation Y, we're going to miraculously get a good estimate of our output X. Okay, so this is kind of a schematic of model-based processing versus deep learning. So how would we go about merging them? Well, today in the talk, we're going to talk about two methods. And again, like I said, these are methods that many people are working on. So the first is this method of deep unfolding or unrolling, where basically we're integrating model-based algorithms into deep networks. So the layers themselves are going to look like an iterative algorithm. The second approach is going to be the reverse. So we're going to actually start from the model-based algorithm, and just every time we encounter a block that depends on something that's unknown, we're going to substitute that block by a small deep network. Okay, so we'll talk more about these approaches, but these are the two main approaches that we're going to focus in this talk to integrate model-based processing with deep learning. So just 2 words more about each one of them. And of course, we're going to go into more detail throughout the talk. So deep unfolding is really, I think, a beautiful method that originates back to the paper about 10 years ago of Gregor and LeCun, and then followed up by many researchers who have been expanding this idea, where the idea is to take our iterative algorithm that we showed before and explicitly write out a small number of iterations. So at least in the examples we've looked at, we've never used kind of more than 10 iterations. So really a small number. Now here, we still didn't do anything. There's no learning. This is still just 10 steps of an iterative algorithm. But then in the last step, what we're going to do is in each one of these steps, we actually have parameters that depend on the channel or on the model. What we're going to do finally is free those parameters, meaning in each one of these layers, we're going to learn those unknown parameters from the data. So what we end up getting is a deep network that's quite shallow, where each layer looks like an iteration in a well-known iterative method, but we're going to learn part of those parameters rather than keeping them fixed as we would in an iterative algorithm. So this is the basic idea of deep unfolding. And for those of you interested, we have a recent review that just came out in Signal Processing magazine together with Professor Vishal Monga and his former PhD student Yilong Li, which kind of goes through these ideas in more detail. The other method we're going to look at is kind of the opposite. So here we started with an iterative method and used that to develop a deep network. In the second approach, we're going to do the opposite. So we're going to look at problems where we have very good model-based algorithms that are not necessarily a solution to an explicit optimization problem, but just algorithms that we know that are very good, like dynamic programming, for example. And then we're going to look at them, and anytime there's a block that depends on something we don't know, we're just going to replace that block by a small deep network. And sometimes this deep network is actually just a layer or two, so it's quite shallow. So we're not doing end-to-end learning. We're not replacing the whole algorithm by a black box. We're only replacing the block that depends on something we don't know. So we still keep the flavor of the underlying algorithm, but we, again, allow learning in places where there's unknown parameters. And here again, for those who are interested in more details, we also have a recent review on this approach, which we've been using primarily in different communication problems. So that kind of summarizes, the basic philosophy of what I'm going to be talking about today, and what we're going to do in the rest of the talk. And again, hopefully my voice will carry through to the end, is to look first at applications of this idea of unfolding to different problems in imaging, both for deblurring, for ultrasound imaging, and for super resolution. And in the second part of the talk, we'll talk about this plug-in approach, which we've been looking at primarily for communication problems, and we'll look at some variations on well-known communication algorithms that we could get using this approach. So I'm going to start by deep unfolding, but if anybody wants to ask a question on the basic philosophy, I'm happy to take any questions before I go into more details. Okay, so no questions yet, so let me continue. So let me just reiterate this concept of unfolding, which was really nicely outlined in the original paper by Gregor and LeCun. So like we said, the idea is to take our iterative algorithm and each iteration to explicitly write out, and then take that iteration, which here is marked by some function, and look at the parameters that it depends on. So for example, these parameters may be a PSF or a channel. And then what we're going to do is we're basically going to learn these parameters. Instead of assuming that they're known and fixed, we're going to learn them. And typically we're going to untie them, meaning in each layer, we're going to allow them to be different. So it's not like we're estimating a channel or a PSF and plugging it in. We're actually allowing it to vary from layer to layer. So just to make this more explicit, we could look at the sparse coding, which leads to the well-known ISTA algorithm from the original paper of Gregor and LeCun. So I'm sure everyone here is familiar with the basic sparse recovery problem, where we assume that we're looking for some sparse vector X that's measured through a linear system with some additive noise. And probably one of the most popular methods for recovering X is the well-known L1 regularization. And the idea is that we have an L2 error, which is our measurement error, and then we have an L1 prior on X, and basically we're looking at a point that's going to minimize some weighted sum of these two objectives. So one of the most well-known methods for solving this is the iterative shrinkage and thresholding method, ISTA, where basically we take a gradient step towards the error criterion, and then we move it in the proximity of our regularizer. So this leads to the well-known ISTA method, which was first illustrated by Deblurring, and it's a very simple and intuitive algorithm. So we take our data Y, we apply a scaled version of our assumed known transfer function. We then iterate where we have soft thresholding and a gradient step where we subtract kind of the previous iterate. So these are the conventional steps in the ISTA algorithm. And what we do to develop LISTA, which is learned ISTA, is that we take this basic block, we're going to write it explicitly k times, where again, k is usually a very small number. And then the important second step is that these blocks that are fixed here, right here, we assume that A is known and that we use some fixed mu, which is, the step size. Here, we're going to learn these blocks, and you can learn them in different ways. You could assume that this is a convolutional layer, so you could restrict them to be convolutional. You could tie them, right? You could assume there's a known relationship between them where you could untie them. So there's, of course, some games you could play here, but at the end, this leads to a very powerful network that's interpretable, right? We know what each layer is doing. The layer has to do with the underlying optimization problem, and it's going to be very efficient because it's not going to have a large number of parameters. So this is the well-known LISTA algorithm and the basic kind of running example of unfolding. And what we want to show next is how we could expand this to many other problems and algorithms. So I'm going to give some examples, and I'm going to start with examples in standard imaging, and then we'll move on to examples in ultrasound. So I think there's a question in the Q&A.
Yeah, so the question is from Ashutosh Soni, and it is, will the benefit of having deep networks fade away when we use shallow networks in the model-based approaches?
Yeah, so that's a really good question. So thank you. So, what we find is the opposite, right? The advantage is we actually get better performance than, a large deep network because we use fewer parameters, but of course we're incorporating knowledge about the problem. So because we're using knowledge, we could get away with fewer parameters. Now, of course, we could always make the model-based approach deeper. The advantage is that we don't have to, that even with the small number of layers, we actually get really good performance. So I hope that addressed the question. So the first application I want to show is to image deep blurring, and this is again a collaboration with Vishal Monga's group. So here we looked at the most standard deep blurring problem where we have a blurred image. We don't know the blurring kernel, and of course we also have random noise. And we use the basic notion of unfolding, but we did it, of course, in a little bit more sophisticated fashion. So let me just briefly describe the main idea here behind our unfolding method. So what we want to do in this blind deblurring is we'd like to find both the kernel and features. So we're going to do this in a feature domain. So we'd like to find features that are going to match filtered versions of our measurement. So for example, we may want to do this in the gradient domain or in some other weighted gradient domain. So what we're going to assume is that we know in advance the features that we're interested in. So for example, it could be the filtered versions that we want. So F, for example, could represent the gradient in 2 dimensions or in 3 dimensions. And then ideally, we'd like to solve this minimization problem where we want to find both the blurring kernel and the desired features. And, here we add simple regularizers. So we want the kernel, to have finite L2 norm. We regularize it, for example, to be positive. And we have a sparsity constraint on our feature vectors. And then once we find the feature maps, we could go ahead and extract our image by a simple least squares criterion where we want to fit both the measurements and the filtered versions of our signal. So you could use your favorite algorithm to kind of solve this optimization problem. Specifically, we looked at a variable splitting approach, but of course you could use other iterative methods. And then what we did is we unfolded it into a deep network where we didn't assume that these filtered versions were known in advance. So basically, we're learning these filtered versions because in practice, we don't know if matching the gradient is the best or some other filtered version of Y, and therefore we allow ourselves to learn this in the process of the unfolding. And what we find is that this really leads to very good performance. So here we compared what we get with state-of-the-art methods that train on a much larger database. And we see that with the simple network that doesn't have a lot of layers, we can actually get much sharper images and much better performance than we get with competing methods that are much more complicated and train on much larger databases. So all the code is available. And of course, the details of exactly what we simulated could be found in our paper and in the online version. So this is really a simple application that shows kind of the power of this idea. A second problem we looked at in the context of ultrasound is doing robust principal component analysis. So here we were motivated by a problem that appears a lot in ultrasound, where basically we want to separate background from flow. So in this case, we're looking at blood flow, or we're trying to look at blood flow, but we get very strong reflections from the tissue. And the problem is to separate the two so that we could see the blood flow. Now, the standard approach here is to use PCA or SVD filtering, right? Where basically the assumption is that the tissue is going to have strong singular values, and therefore we could just remove them. But that is actually not strong enough, as you can see over here. There's a lot of background when you do that. So what we propose to do instead is to use a low rank plus sparse model, where we model the tissue as low rank and the blood flow as sparse, and then unfold that into a learned robust PCA version. So we worked on this problem in 2018, way before Corona and COVID. And at the time, we called this method convolutional robust principal component analysis, which we abbreviated to Corona. And it looks like that method went viral, but this was in 2018, so we didn't know about Corona then. So I'll explain this method in more detail. Those of you interested in the ultrasound applications, we have a recent review on deep learning for ultrasound where we go into more detail on these and several other applications to ultrasound imaging. So the idea is, again, very similar. We start with a standard robust PCA problem. We're going to assume that we could write our data as a sum, as low rank tissue plus the sparse blood flow. We have, a low rank constraint on the low rank part. We have a sparsity norm on the sparse part. And if you would just solve this, for example, using proximal gradient scheme, you get iterations between singular value thresholding and standard L1 thresholding, or mixed L1, L2, depending on how you modeled it. And you would get a standard iterative algorithm where you have two inputs in every layer, right? We have both the low rank component and the sparse component, and these have different thresholds and different linear operations. Okay, so this is just writing out one iteration in this proximal gradient algorithm. But already you see that this looks very different than a standard deep network, right? We have two inputs that are going through the network. There's kind of this cross over between them. There's different thresholding in each one. So this is already becoming interesting, right? It's moving away from ISTA, which looks quite similar to standard deep networks, and it's starting to look already very different. So now we can move from this ISTA approach to the robust PCA approach and then the learned part. So what we're going to do quite naturally is take all of these layers and substitute them by learned convolutional layers, which is why we call this deep convolutional robust PCA. And then we're going to write down, 10 layers and learn it end to end. And this leads to this Corona method, this learned version of robust PCA, which does a really good job, as you can see over here, in separating the blood flow from the background. Now, the really nice thing about this method and other model-based methods is that they really don't need a lot of training data. So here we did the training data on 20 frames. That was it. So really small number of training images was already enabled us to get very good results. Another thing just in the area of ultrasound is going back to basic beamforming. So, all images or most images in ultrasound are formed by beamforming, where, you could use delay and sum beamforming or minimum variance beamforming, but these are kind of standard closed form solutions for beamforming. And instead you could use adaptive beamforming, where you keep the beamforming scheme. So again, it's model-based, but we learn the weights from the data. And as you can see over here, again, it leads to very simple methods that have really good performance. And just the last thing on ultrasound, and then I'll take questions. Because now we could do this beamforming in different ways, in different model-based ways, we actually have access to different data than people had before in ultrasound. Because before, all you had were these delay and sum images that you couldn't play around with because you couldn't go back. But now we have the ability to actually look at the original data and combine it in more interesting ways. And this actually gives us different clinical applications that we couldn't do before. So it's not just about maybe learning more efficiently or learning from this data, but it actually enables different clinical applications that were simply not possible before. So let me stop here. I see there's a few questions, so I'm happy to take some questions.
Okay. The first one is from Rahul Mahadik, and I'm going to give the audience an option to speak up if they would like to follow up. So the comment is just, but the deep networks actually extract multiple features in more sophisticated manner than shallow network. It seems like a comment more than a question.
Yeah, so this is similar to the previous comment. So first of all, you see the results, right? The results are better than deep networks that have tens and even hundreds of layers. So at the end, the proof is in the performance, and the performance is much better. But to explain again why we're getting better performance, standard networks are not given any information, right? They're basically trying to learn everything on their own from training data. When you use a model-based approach, you're entering a model, right? So you're guiding the network in some sense towards the areas that you'd like to be. And that has a lot of power, right? So that's exactly the point of model-based AI, is that giving it models is a lot of power. The performance is not worse, it's better.
Okay. The next question is by David Morales, and that is, the network learns a different kernel in each layer, or is just one learnable kernel used in each step network?
Yeah, that's a really good question. So this goes to the general question, if I could phrase it. And again, I do apologize. I see my voice is fading, but just to phrase that really good question more generally, you could ask, this has to do with if I tie the layers or don't tie the layers. Like, do I want to, at the end, learn a kernel, a PSF, a channel, or do I want to get good performance on the metric that I define? So, there's different approaches depending on the application. In the deep learning application, we looked at, we're not actually interested in the kernel. We're interested in the underlying image. And therefore, we did not tie the layers. We allowed ourselves to learn a different kernel in each layer. But if you were interested in recovering the kernel itself, then you would tie it so that you could get one kernel. And this is true more generally.
Okay, thanks.
Okay, that was David. David, did you have anything else to follow up? Perhaps not. So we have two more questions. Yonina, would you like to go through them now and then continue, or would you like to?
I mean, let me maybe try to address them briefly, just so that we could also continue. So, and I just opened the Q&A, so I could, if it's okay, I could address them briefly. So one was about beamforming, if we operate in the covariance or the MVDR. So again, that's another good question. We could do it either way. I think that would be part of the model-based. You could take model-based also to the input, right? You can say, I know working on covariance is good, so let's do this in the covariance domain. And you'll see shortly that this is what we do for super resolution. So yes, if we think covariance is better, we could operate in the covariance. Specifically, we didn't do that because in ultrasound, I won't go into that here, but in ultrasound, there's reasons not to do it because you don't really have multiple data instances to have good statistics. So in ultrasound, we don't do that. But if we were looking at radar, for example, we do that. So that's another model-based point. The final questions, what were the requirements on the training data? So another really good question. So, again, okay, what training data and how much is an open question in general in AI. So we don't have a very specific answer in this context either. But what I can say is what we found is that we can use very little training data, and we also generalize better. So even when we use training data in one scenario, we were actually able to generalize quite well. And we'll see that when we get to communication in other scenarios as well. So we don't have like a closed form formula, but we've seen that we could get away with much less training data and much less diverse. Here you'll see when I talk about super resolution, we do training on a single image and we get really good results. So let me move forward if it's okay, just so that we could end on time. And then I'm happy to, of course, take more questions afterwards as we go through.
Hello.
Hi.
Yes, can I have a quick follow-up on that training data? Because in signal processing, pretty much we're looking at the signal structure for model-based. So for training data, if you have a particular signal, how can you assure that it will capture that the signal structure is not overfit to a particular training signal?
Yeah, okay, so good question. So, the point in the model-based framework is that you're using models that are very generic. So it's not a model for a specific signal. Okay, so for example, like if you look at the Deblurring algorithm, basically what we assumed is that there is a linear relationship between the input and output. Now, even if that's not exact, you could still apply the method, but it's not like I'm assuming I know the precise linear relationship. So these are models in a very generic term. I'm not assuming something very specific about the signal. Okay, but at the end, it is model-based, right? Like in robust PCA, I'm assuming that I'm trying to separate two things. If I'm not trying to do separation, then it's not the right network to use, right? So, I have to know what I'm trying to solve. But the point is, if I'm trying to separate, I'm not going to download a ResNet that was developed for a totally different problem. I could target that separation problem. So that's basically what we're saying.
Thank you.
Okay, great. So let me move on maybe to the next application. And again, I'm really happy to take questions. I just want to try to, basically end on time, and then, we could take maybe one or two as we go through and then do the rest at the end. So I want to touch quickly on super resolution in microscopy. And this is a really nice problem, I think. So we know that microscopy is probably the most convenient imaging modality, but it's limited by Abba's diffraction limit, which means that we can see details that are smaller than half the wavelength that is used for illumination. So in the optical domain, we could see, for example, bacteria, but we won't be able to see proteins and small molecules. Now, one of the really, really clever and nice methods to try and overcome the diffraction limit is super resolution microscopy using fluorescence microscopy. And this is a really good idea. And we know it's a good idea because it won the Nobel Prize in 2014. And the idea is that we enter fluorescent molecules into whatever it is we're trying to image. And we control the fluorescence so that instead of taking one image, we take thousands of exposures, where in each exposure, only a small number of fluorophores are actually fluorescing. So it's a chemical process that we control. And the advantage is that if in each image, we only have a small number of blinking points, we can localize them, right? Like just think of sticking a Gaussian every time you see something fluorescing, and then you sum over all the exposures and you'll get one super resolved image. So it's a really good method. It won the Nobel Prize. It obtains a factor 10 improvement in spatial resolution, but the limitation is that this is done at the expense of temporal resolution. So now, instead of one image, you have thousands of frames. And clearly, if you're trying to do live cell imaging, you can no longer do that because the cell is going to move. So of course, it assumes that things are stationary. So the question is whether we could get both high temporal resolution and high spatial resolution. So to do this several years ago, we've developed a method, and this is before we did learning. So this was a model-based approach, where basically we looked at doing super resolution in the correlation domain. So this ties nicely to the last question of looking at correlation. And we wanted to look at sparsity, but not in the image domain because it wasn't powerful enough, but rather in the correlation domain. So the idea is that these fluorophores, when they're blinking in an independent fashion. So first of all, there's a small number of them. So of course we have sparsity. But the second advantage is that if we look at their correlation, because they're independent, the correlation matrix will actually be diagonal, and the diagonal itself will also be sparse. So this gives us additional structure that we could exploit. And it also gives us denoising, because when you compute the correlation, you're smoothing out the noise. So this turned out to be much more powerful than just conventional sparsity. So several years ago, we developed this method called SPARCOM, super resolution correlation microscopy, where basically, as you saw in the previous slide, we're solving a sparsity problem in the correlation domain. And the nice thing is that it really gave us really good resolution. So here we're comparing our method SPARCOM with STORM, which is the method behind the Nobel Prize. In this case, we have a ground truth. This is what you see from a standard microscope. And you see that we get better spatial resolution than STORM, but we're using 2 orders of magnitude less images. Here you see that we can actually get better spatial resolution. So here you see a cavity that you can't actually see in the STORM data. So we could get very good performance using 2 orders of magnitude less data. But the disadvantage of this approach is that we had to assume that we know the PSF, okay, because it's based on modeling and we needed the PSF knowledge, which you don't always have in standard imaging, and it could be hard to estimate. So the next step was to take this optimization-based approach in the correlation domain and unfold it, just like I've been describing before. And this is what leads to what we call learned SPARCOM. So here you see the performance of learned SPARCOM. It gives us even better performance than SPARCOM in terms of spatial resolution. But the important thing is that we didn't use any knowledge about the system. And all of this training was done from a single image. So we took a single image. It was a simulated image. It wasn't even a real image. We used a single simulated image to train the network, and it was powerful enough to work under different scenarios and different PSFs. So again, I'm not going here into all the details. Those of you interested can see the paper, but it shows some of the power of this model-based framework. So again, we are using knowledge, right? We're assuming the fluorophores are blinking independently. That's a model-based type knowledge, but it's really a relaxed type of knowledge that makes a lot of sense, and it's very powerful when we incorporate it into this learned version. Now, what's really nice is because we could do this now very quickly, and we don't have to know anything about the system. And quickly, I don't mean computationally. I mean, we only need a small number of images. We can now use this for live cell imaging, which you couldn't do before. So this is collaboration with a group of Professor Oran, Gilad Aran from Weizmann, where for the first time, we're really using this fluorescence microscopy idea for live cell imaging. And we have initial results. We just submitted a paper about this. So, once the results are confirmed by the biological community, I'll feel more confident to go into them. But basically, we were able to observe biological behavior that couldn't be seen before because the time scale was just too fast. So now we could use this for live cell imaging. Another application that is taking the same idea that we're also very excited about is actually a clinical application of the very same idea. So we saw before how we could use this for microscopy. Our next step was to use this for ultrasound. Now, of course, in ultrasound, you can't inject fluorophores, or you don't want to inject fluorophores into people's bodies. But what you can inject are these microbubbles. So this is SonoView. These are bottles that we have in our lab. They're FDA approved. People use them for contrast enhancement. So it's not our invention to use these bubbles, but we use them for super resolution. So what we do is we inject these just like a regular infusion into the bloodstream, and then we use a conventional ultrasound machine. So this is what you would see. You don't see anything very interesting, but now we use the exact same method. So again, we use this independence idea and this localization idea to develop a learned framework in order to recover the images. And in this case, in this context, my students call this method SUSHI, Sparsity-Based Ultrasound, super resolution hemodynamic imaging, because we're trying to look at blood flow. And actually, the first time we presented this at an ultrasound conference, someone said that it's a very fishy method. So I like that. But it does look fishy because you get really good depiction of blood flow, which you can see in the standard method. And recently, this was results from about a year or two ago. Very recently, we started looking at using this on true clinical data. Okay, that was more phantom data. We started with animals. So we started by looking at a rat spinal cord, and already you can see that you could get very good resolution. But the most exciting, at least for me, was a study that we've done very recently with Beilinson Hospital. So we scanned 20 patients with breast cancer. And we wanted to see if using this method, the doctors will be able to see details about the tumor that they can't usually see with ultrasound, and therefore have to send the patients to much more extensive imaging. So, this is the machine and the bubbles, leaving our lab. These are the doctors we're working with. This is the scanning of the patients. And I'll just show you 2 examples so you can see the power of this framework. Now, it's important for me to stress, we had no prior data here. So training was not an option. We never took breast cancer patients' images before, and we didn't want to bother them with training data, etc. So all of it's when I say training on a single image, it's basically no training because I'm training on the actual image. So there's no prior training done in any of these examples. Okay, so in that sense, you could call it unsupervised, although we're using a supervised idea, we're just not using prior images. So this is patient number 2, who has apparently a fibroadenoma. What you see over here is what you see in standard ultrasound machine. Here you see different super resolution methods that have been used in the literature. This is kind of the state of the art. I'm not going to go into what it's doing, but again, you see that it doesn't actually give you more detail about the tumor. And this is what we get from our unfolded version. You get very good display of the vascularization. You see a satellite tumor over here that you can't even see in the original image. So actually the doctors were very excited about this image. It gave them a lot of clinical information, which they validated. These patients all had more extensive MRIs, PET CTs. So we were able to validate the results and to show that these images are actually the correct ones. The second patient had a malignant mass. And I think what's interesting is that if you look at the mass on a regular ultrasound machine, it looks the same, right? I mean, all you see is a black hole. You can't see the difference between them, but you see that using our approach, there's a big difference between these tumors. And again, the way the vascularization is performed here at the edges of the mass and the low concentration of blood vessels in the middle is very informative for the clinicians. And this is what helps them determine that this is actually a malignant mass. And again, this was confirmed later with biopsy. So this shows, a little bit of the power of this framework. We're essentially not using any prior training data, and you get really good images. And we did nothing particular to form these images. It's a standard ultrasound machine besides injecting these micro bubbles. So that's kind of the first part on unfolding. I see we're a little bit short on time, so maybe, and I see there's also questions in the Q&A. So maybe in the interest of the audience, maybe I'll just take a few more minutes to get to the end, and then I'm happy to stay as long as needed to go through all the Q&A. But those that need to leave on the hour will be able to leave and at least see a little bit of the end. So let me quickly go through the communication approach. I imagine most of the community is more image oriented anyway, but I do want to show the second approach. So let me maybe skip some of the communication details. The goal is that we don't want to just take, just like in imaging, we don't want to take the communication channel and replace it by a standard deep network. We want to do something that's tailored to the problem, tailored to the knowledge, and goes back to optimality when we know the channels. So, there's been many approaches to do generic deep learning over communication channels. One of the really, really nice papers and kind of the first in this area was a paper by Andrea Goldsmith and her former postdoc, Nariman Farsad, where they looked at developing a deep network specifically for symbol detection. But again, it's not using this model-based approach. And what we wanted to do is try to get something that's interpretable, could adapt really well to channels that are changing, and could work on very small training sets. So what we did is the approach we showed before, where basically we take a standard method and we replace the steps that we don't know with a shallow deep network. So in this case, we use the Viterbi algorithm. The Viterbi algorithm is the most well-known algorithm used for symbol recovery. It's basically dynamic programming, assuming a state space models, a model that of course made Viterbi very successful. He established Qualcomm, and here he's getting the Medal of Science from George W. Bush. So, definitely a very important algorithm. We didn't use unfolding here because it's not going back to an original optimization algorithm. It's an efficient method. That the only problem with this method, and again, in the interest of time, I'm not going to go through all the Viterbi algorithm details, but let me already skip this, just shows what Viterbi does, but I'll skip to the next slide that shows it kind of on a high level, right? It's dynamic programming over a known graph. But what's important is that what depends on the channel is this likelihood computation. So basically what you do in Viterbi, every time a symbol comes in, you compute its likelihood based on where you are right now in the trellis. You compute the likelihood to move to the new state, and then you're going to just keep the path with the largest likelihood. So all of this dynamic programming part has nothing to do with the channel, right? So you could keep all of this, no need to replace all of this with a deep network. The only thing that depends on the channel is this likelihood computation, which allows you to score these different branches. So what other people have done is basically replaced all of this with a deep network. What we're saying is, let's leave all of this. All of this is good. The only thing we need is the likelihood. So let's just replace the likelihood computation with a network. And that is really easy to do because computing likelihoods is something that we do in deep networks all the time. So we could think of this as a classification problem and just use the simple softmax, or we could think about this as a regression problem and estimate the parameters of the unknown likelihood. So either of these are very simple. We actually do both. They lead to similar performance. And in both cases, we use 2 layers. So really simple deep network that's actually quite shallow. We keep the bottom part, we keep the whole trellis part, and we just use that to learn the likelihood. And not surprisingly, it leads to very good performance. In fact, the nice thing is that it generalizes really well. So even when the channel changes, and it's not a channel that we trained on, we still get very good performance, and we approach the performance that we would have gotten with Viterbi if the channel was actually known. So this is in the context of Viterbi. We could do the same thing for factor graph method. So again, I won't go through the details. Viterbi basically solves the likelihood problem. You could also solve a maximum posteriori problem, which has to do with factor graphs, which allow you to take an arbitrary probability function and factor it into smaller conditional probability functions, and then you can compute the joint likelihood by passing messages over the smaller graph. So there's many algorithms out there that are basically factor graph methods. And again, the message passing itself does not depend on the channel. The only thing that depends on the channel are these actual factors. So again, instead of replacing all of this by a deep network, we keep the message passing and we only replace these factors by a learned network. So it's going to look like this, right? These nodes are replaced by small networks, but the whole message passing function is kept. It remains the same. And this allows us to do map learning instead of likelihood learning. So in the context of communication, when we do map, it's called the BCGR method, and therefore we call this BCGR net. But you could use this for any algorithm that relies on factor graphs. So again, we get really good performance. Of course, it works better than Viterbi because it's maximum posteriori and not maximum likelihood. It's very efficient. It could adapt to unknown channels. And we can use this in problems that have nothing to do with communication either. It's just a way to solve computation of joint probabilities over a graph, which we may not know in advance. So finally, just the last slide in this context is that another method that people use a lot in communication, and again, it's not an optimal solution to any problem, it's just a very good heuristic, and it's kind of resembles like the OMP method in sparse recovery. So it's an iterative decoding method where basically you do successive interference cancellation. So you find the strongest user, you remove it, and then you keep on going. And this is really useful in channels that are complicated to work with analytically and where you have multiple users with different SNR. So it's a really convenient method. But again, this removing the user and removing it with the right weight depends on knowledge of the channel. It also depends on assuming you have a linear channel. So here again, we can use this model, this idea in a model-based fashion where we learn that weight from the data, rather than assuming that it's known, but we keep this successive interference framework. So it's going to look the same, but we have this adaptive weight that we learn from the data that we're actually given. So let me just end by saying we've been using recently similar ideas to address various problems in COVID. So we have a task force that was formed here in Israel with various different hospitals and AI experts to try and help the hospitals when COVID started in detection, both from X-ray and from ultrasound. PCR results only achieve 70%. They take a long time, and they also can't monitor the disease. We've used a very similar idea where basically the point is to train a network that could detect COVID, but we enter further features into the network, not just the data itself. And we're able to get over 90% detection when we look at X-ray. we're able to get close to 80% detection in ultrasound, which is really good for ultrasound because ultrasound is actually quite hard. It's actually not used anywhere in the US as far as I know for COVID because it's so hard. In Italy, they used it a lot. And here we've been collaborating with a group of Professor Libertario Demi. So this is an area where they used it a lot. In Israel, only 1 or 2 hospitals use ultrasound, again, because of the difficulty. But we see that by entering this model-based approach, we could actually get really good performance. And we're now looking at implementing this within the hospitals. So to sum up, and I hope I'm ending on time and then really happy to take questions, what we try to promote, and again, there's many other people working on this, of course, is trying to bridge these ideas of machine learning and signal processing, where the goal at the end is to get efficient, interpretable methods that could train from small data sets, could be very adaptive, and also give us more insight into what these methods are doing. I do want to say that what's missing, what you didn't see in the slides, and that's because very little is known about it, are theoretical results. So what we're finding is that these methods work very well in practice. You know, I've showed a subset of examples in our reviews. You could find more details. They appear to work really well. We have some specific analysis for very specific settings, but in general, like everything else in AI, it's very hard to prove, you know, why they work, we understand, but what do we mean by work? Could we prove analytically, you know, that a small set of training data is enough? These are really open questions and really exciting questions because we see that it works well in practice. So this is something that personally we're very interested in. And if anybody is interested, I'd be super happy to collaborate and to talk more about that. So of course, you know, none of these results would happen without my team and my collaborators. So I mentioned the collaborators throughout the talk. I'd like to acknowledge them again. And of course, to acknowledge the students who were brave enough. We had an outdoor trip. Many were too afraid due to COVID, but those that came are here in the image. And thank you very much for your attention. And as I said, if anyone finds these topics interesting, we're super happy to collaborate and especially to try and better understand the theoretical properties of what we actually observe in practice. So thank you very much. And again, I sincerely apologize for my sore throat and hopefully you were still able to hear me. So I'm happy to take questions.
Thanks, Yonina. That was a wonderful talk, and I don't think I ever noticed that you had a sore throat. so,
I definitely talked slower than usual. So
yeah, but I think it was still great. Lots of good stuff for our audience, for the computational imagers out here. We have a lot of questions for you, so that shows people were tuned in.
Okay, great. Happy to try to answer them.
We can go as long as you like. Sometimes we keep getting more questions and, you know, so we then have to put an end at some point. The first question is by Ashutosh Soni. What was the amount of training data and time required for this generally? I don't know which specific thing he's talking about, but I can also enable him to speak if you'd like.
Sure.
I'm audible.
Yes, we can hear you.
Yeah, actually the question was answered by her, but the question was like she mentioned the training data was just 25 frames or so. So I was curious, what amount of training data in general does it take?
What amount, sorry? Sorry, I didn't hear the last part of the question.
Yeah, so I was asking, like, you gave an example of 25 frames of training. So in general, how much data or time does it take? That was my question.
Yeah, so, but okay, in terms of data, again, like we used 20 images because that's what we had. So the results I showed were from 20 images. I think like any question in training, you know, deep networks, we don't have a formula, right? Like, you know, I don't know how many are needed for good results. What we show is, for example, in that case, we had 20 images. In the optical case, we had a single image. So again, I think we don't have a theory that's going to tell us how much we need and under what circumstances. that's part of what I defined as, one of my motivations to talk about this is actually to try and get people interested and to maybe collaborate on some of these aspects. So we don't have a theoretical result saying in this scenario, you need these many training samples. But what I've showed are results of, this is what we did, and you can see that it works quite well. So I hope that addressed your question. I imagine that many of the questions in the Q&A, maybe I could try and give, because I'm just briefly going through it, and there's quite a few questions, that are repeating this, and it's totally understandable, right? Like, we'd like to have a theory that says, you need these many training samples, you need these many layers, etc. So, like I said, I mean, part of the reasons that I really wanted to talk about this and not about something more established is because I think it's really interesting, right? Like, what we're showing here is, there's ways of combining models with deep learning. They lead to advantages that you can see, right? We need small amounts of data. They generalize well. They're interpretable. So it looks really encouraging. What's lacking is a good substantial theory that gives answers to these questions of, how well could I generalize? How many iterations? How many layers? We don't have those results right now. It's basically trial and error, or just trial, because like in ultrasound, we don't have images. So we just have to do with what we have. Now, maybe if we had, many images of a certain tumor, we would do better, but we didn't even try going there. And the reason is A, because we just don't have them. B, because most of the clinicians that we've spoken to don't want that. They're very afraid of learning things from one patient to another. And we figured if we could do it without carrying information over from one patient to another, then that's much better. So that's what we did. So again, I see there's quite a few questions that, go back and forth to this more theoretical understanding, which is exactly what I think is lacking. And again, anyone who's interested, please send me an email. I'd be super happy to have a more focused discussion on how maybe, we could bring more theory into these types of results, but we don't have it right now.
Okay, I also added in several of I think all the people who are asking questions to the panel, if they would like to speak up. And Yonina, you said, were there any questions in particular we should go through, or what would you like to do?
Okay, so maybe I could take, I see like my my voice is like totally fading. Let me just try to take a few that look maybe different, not on this question of layers. Not that that's not an important question. I think I've addressed that. So let me just see if there's something here that's different. Oh, well, it keeps on jumping. There's more and more questions. Okay, so here's an interesting, all the questions are interesting, but here's one that's different than what we saw before. So there's a question here about, is model-based learning like inductive bias? That putting in the context of bias variance trade-off, will the model-based deep learning pay in high variance when moving to a setting where the model is not adequate? Okay, so really, really good and nice question. So I think, yes and no. So yes, in the sense that, of course, what's giving the benefit, there's no free lunch, right? And that's the point. I think models are good. So of course, we're benefiting from the fact that we are entering knowledge into these problems. And if we move to a problem where it's highly not relevant, then it's not going to work. So if we take, for example, the microscopy case, and we're assuming that blinking is independent, and suppose it wasn't, right? In that case, it really physically is, but assume it wasn't, then if it's just a little bit correlated, probably things will still be okay because training kind of compensates. But if it's highly correlated, I'm sure it's not going to be a good method. And in some sense, that's what we want, right? I think what we're saying is, there's problems where there's basic things about the problem that some people could argue it's prior information. I would argue it's not prior information, it's just the problem. Like assuming fluorophores blink independently, you could identify that as prior information, or I could say, no, it's just the chemistry. It's just always going to happen. So why ignore that? Now, of course, if that wasn't the case, then this is not going to be the best method. And probably a generic black box AI would do better, but it would require a lot of training data. So I think this is a really good kind of question and answer at the same time, right? It is assuming something about the problem. The point is that it's assuming something very relaxed about the problem. So if we look at communication, Viterbi, BCGR, factor graphs, all of these assume that you have a finite state machine, okay? So that you have finite memory on the channel. Now, if you don't have finite memory, they're not going to work. And therefore, the learned versions of them are at some point going to fail as well. So maybe they'll work better than the non-learned versions, but at some point they're going to fail because they're based on finite, memory in the channel. But again, reasonably, in any reasonable communication channel, that's going to be the case. So it's kind of like, why build a network that can look for every possible scenario under the sun, but therefore is going to require a lot of training data and is not going to generalize well, when I could use basic assumptions about communication or about radar or about ultrasound that are really basically true, and that will aid my algorithm. So in that sense, you could think of it as kind of inductive bias or bias variance trade-off, but I like that analogy. I just think it's kind of like on one level above, meaning it's not on the level of assuming something very specific about my specific problem. It's assuming something about the overall setting of the problem. Okay, so something about the communication network, right? Rather than like the specific data or the specific channel. So I hope I addressed that question. It was a question by Elvin. I hope I addressed that fully. If not,
yes,
then,
thank you. Thank you so much. That was a very good answer. Thank you.
Okay, great. How do you make the trade-off between, oops, sorry, jumped, interpretability and performance? So let's say if you know the kernel, if you want to estimate the kernel, you're going to make it shared. What about changing the internal layers to become more neural network-like? Yeah, okay, so another really good question. So I like to view these ideas as a continuity, okay? And that's, I think, the beauty of them, again, in my perspective. So I like to think of it, on one end, we have the model-based approach, where if we know what it is we don't know, whether the channel, the PSF, whatever it is we don't know, then we know the best solution to the problem, right? We have a given algorithm that works well. Either it's optimal or experience has shown it works well, but we know what to do when things are known. And then we move to a scenario where things aren't known, or things are changing, or things are varying. And what we want to do, in my opinion, is move gradually, right? So we want to say, okay, we're going to move away from this known solution, but we're moving away, in a controllable fashion. So we don't want to jump. We don't want to say when everything is known, we do this. When we have some uncertainty, boom, we do that. But rather we do this, and then we're going to move gradually. And of course, there's an art to it. It's not just science. And I think this question is hitting at that, right? I could decide at each point what I want to learn and what I want to free. And there's a trade-off, right? If I have more training data, I could free more parameters. If I have less training data, I should probably free less parameters and use whatever knowledge it is that I want to use. It also depends on the goal. Again, do I want to learn the output? Do I want to learn the PSF? So this is part of the art of using these methods. But I think, at least to me, the nice thing is that this part of the art really depends on your knowledge on the problem. So it's not just random, right? Or it's not just like, I'm going to set the parameter at 3.7 and see how it works. You have good reasons to make these selections, and these reasons are coming from knowledge of the problem. So I think, again, we should bring that knowledge into the problem. To me, that's an advantage. And I'm not saying this is true in any problem. Again, going back to problems that are very hard to model, the black box methods are probably the way to go. But here I'm talking about problems where we know a lot about them. And therefore, in my view, we should use that knowledge. We should also use learning, because learning is clearly a good thing. But again, the point is to try and do both. So I hope I addressed that. Tao, that was a question by Tao. I hope I addressed that question.
Yes, thanks.
Okay, great. Okay, wow, there's a lot of questions. So maybe every time I read it, something else pops in. So maybe whoever wants, maybe just open the mic and ask. I think that's going to be easier.
Okay. Hello, can you hear me, Yonina?
Yeah.
All right, thank you. That was a great talk. My name is Sundaresh. I had a question. I mean, you did mention saying that somewhere along the top, you did say that you're having this one image from which you're actually doing some learning, right? And this was along
Sorry,
the
I didn't hear you well. Sorry.
You said that there was this one image from which you're actually like doing learning that was in the ultrasound applications, I guess. So I was like wondering as to what is it that you're actually learning from this one image? Is that information that within the image that you're trying to, I mean, to me, it actually looks like that is parameter estimation is what you're actually doing. The whole talk seemed to me like, okay, fine, we are still doing signal processing, but then parameter estimation is where you're actually involving these deep learning kind of methods, and that's kind of evident from that. So again, the question is, I think you kind of answered it, but then my question was like, what happens when you have out of distribution, what do you say, things which are actually coming out of distributions of the model itself? Will the developed model be able to attribute and learn to the out of distribution samples, or we will actually have to, I don't know how that actually works. So I don't know if you can throw some light on that.
Yeah. Okay, great, excellent. So let me just start with your first comment that it looks like parameter estimation. You could say that about all learning, right? Like learning, a deep network in some sense, in the sense you're defining, is also parameter estimation. I have a network, I have weights, and I'm learning the weights from data. So that is also parameter estimation. The parameters are the weights in the network. So in that sense, it's all parameter estimation. All learning is parameter estimation. You're learning parameters. So again, in that very generic sense, yeah, we're doing the same thing. I think the main difference though is that in parameter estimation, you usually will have a small number of parameters and you estimate them and plug them in. So you have a solution based on those parameters. You then estimate the parameters and plug them in. In these methods, it's not what we're doing, because again, we're not actually estimating a parameter because the parameter changes between layers, right? So it's not like if we go to the deblurring example, I'm not estimating the blur and plugging it in to my closed form solution. I'm actually unfolding the network, which in practice is as if I have a different blur in each layer, and I'm learning that end to end on training data. So it's not that I learn it offline, plug it in to a known solution. I'm using the known method to give me the form of the network, and then I'm learning the network parameters from the training data. So it's a more elaborate version of parameter estimation. It's not that I'm learning and plugging in. So I hope that addresses that. It is some form of parameter estimation, which I see as an advantage, right? It's a learned version of parameter estimation, which exactly kind of bridges the gap between arbitrary learning and model-based learning.
Absolutely.
But it is more sophisticated than just learning the parameter and plugging it in.
Got it.
Okay, great. So other questions?
Yeah, thank you.
Sure.
Yeah, hi. I'm Zhe, and I have a question regarding the learning method. So I really like you talk about these unrolling networks. They're really fascinating, but they have to be inevitably affected by the distribution of the training data. So do you know any method of the modern unsupervised learning or the reinforcement learning can aid this kind of problems and combine the model-based methods? Yeah.
So you mean, okay, again, I'm not sure I totally, so I could use model-based methods for reinforcement learning. I guess you're asking the opposite. If I could use reinforcement learning to plug into the model-based approaches?
Yeah. You're correct. Yeah, that's my question.
So, but what am I trying to learn? So when you say I'm going to use reinforcement learning and plug it into the model-based method, I guess in some sense it's a little bit similar, right? Like not the, okay, so I'm trying to kind of digest the question and see if I could give, an answer that makes sense. So I think there's two approaches we outlined, right? One is the unfolding approach where you start from an optimization problem and, that defines the networks. The other is more like a plug-in approach, right? Where I just look at the parts I don't know and, I substitute that with a network. So I think if I understand your question correctly, I think that what you're suggesting could be used for the second type of method. So I could say, okay, I'm going to look at a model-based method. So yeah, a model-based method. And then the component that I don't know, you're saying I could use like a reinforcement learning approach to kind of learn that on the fly if it's going to be changing. So if I understand you correctly, yeah, you could do that. And that would actually be really interesting because it would give you like a model-based online version. Okay. So I think it would be a nice combination of doing model-based and dynamic learning. which could be really nice. So again, I sincerely apologize, but my voice is like totally gone, and it has nothing to do with this talk. I woke up with fever and a sore throat, so again, I apologize. But I hope I addressed your comment, which I think is more a comment than a question, and actually a really good comment, that I can use kind of reinforcement learning to do an adaptive version maybe of this model based. So I think that's a really cool idea.
Yeah, thank you.
Okay. I think we've had plenty of questions, and just to give Yonina space to recover from her throat, and let's probably end it over here. And I would like to thank everyone who asked questions. And if you couldn't get to ask your question, you could. I'm sure Yonina would be fine with answering them over emails.
Yes, and I do have to say again, first of all, thank you again for this opportunity. And I really apologize for putting you through hearing my voice like this, but I didn't want to cancel. I'm really happy that I did it anyway. And I'm super excited about, these topics, and there's so many good comments and questions. And, this is a topic we're really interested in expanding on further. So I'm super happy to, anybody who wants, please feel free to contact me, and, definitely happy to chat over email, and if there's opportunity to think together about different extensions. So thank you so much, and I really appreciate all the questions.
Thanks again, Yonina. For the audience, the next space webinar will be 2 weeks from now, but it'll be on a Tuesday. It'll be on April 6th, and watch out on our website. We'll be giving more details about the speaker and the talk and everything else. So hope to see everyone in about 2 weeks, and have a good week, everyone. Bye.
Thank you. Bye, everyone. Be safe. Keep healthy.